Okay, Assalamualaikum to our panel. For the panel 1 is Dr. Rashid. Panel 2 is Fikri. Today, I, Muhammad Nur Amin bin Haji Kanan, material number B0918103224. I would like to propose to our project title, which is the optimization of steering system for an autonomous vehicle for lane change using MPC controller. Okay, our supervisor is JS Cairo Amiri bin to Sarawak. Okay, this is our presentation outline. For the first part is background study. On the steering system, is made up of the element that permit the driver to change the vehicle front wheel direction. Second is to enable the driver to maneuver the vehicle safely and accuracy. And system mechanism also reduce the driver effort by steering the vehicle smoother. Okay, there are three type of the electric steering in this era, which is, for the first one is electricity powered hydraulic steering, column drive electric steering, and the last one is rack and pinion steering assisted by an electric motor. Next, we move to the autonomous vehicle steering control system. There are numerous methods for autonomous vehicle steering control system available today. Among of them is proportional integral derivative (PID) control, physical control theory (FCT), model predictive control (MPC), and the recent one is the internal model control, which is IMC. Instead of our project title focus on the MPC, so we choose the controller of model predictive control to our project. For the MPC, employ a system model to predict how a machine will develop in the future. It also can organize a multi-input and multi-output, which is a MIMO system, to communicate the input and output and accumulate input and output constraint. For the purpose of the MPC is to optimize process behavior prediction over manipulated input data, and the prediction carried out using a process model, and then the model becoming the crucial component of an MPC controller. For the major component in MPC is we have a model prediction, rolling optimization, and feedback modification. Okay, for the problem statement, back to our focus study. There are several incidents affected by steering control systems, such as misassessing, drowsy, and fatigue. This factor occur when a driver is sleep deprived and does not sleep well, get enough rest before driving, especially on a long journey. Okay, all the factors also supported by previous researcher from SORES 2020. Okay, all of the accident mentioned before the issue gradually eliminate career risk by using autonomous vehicle steering system. Since the system is related to the steering system, it's become the steering. It become the multi-input and multi-output system. Due to the interplay between the input and output, it's not easy to construct the controller for this system using a conventional controller. But by using the MPC controller, we it can overcome this problem. Because the MPC is a multi-variable control system. Okay, for the last of the problem statement is designing the best controller require a larger parameter tuning on a controller to ensure the system fully function. Okay, for the research M, we only have two objective on this project title, which is, for the first one is to investigate the effect of varying MPC parameter such as sample time, prediction horizon, and control horizon. And for the constraint, we have a steering angle, and the second one is steering angle changing rate. For the second objective is to compare the tuning response by tuning the MPC controller with the default response by the previous researcher, which is from the journal. Okay, on this project title, we only focus on the investigating the effect of varying MPC controller that I just mentioned before, which is prediction horizon, control horizon, and sample time for the and next is we only use a controller, a linear controller system, which is a constant longitudinal for an autonomous steering system for controller model. And for the lastly is we only study on 3 MPC parameter like I just mentioned before. Okay, for the literature review, we have a fundamental of MPC, next optimization problem, and the last one is the design parameter. Okay, for the fundamental of MPC, we have two type of fundamental of MPC. For the first one, in the first feature, we have a standard control loop. In the control problem, basically the goal of the controller is to calculate the input variable to the plan. So the input so the plan respond in the way that make its output track the reference output. Okay, for the traditional MPC control, use a feature prediction strategy in order to calculate the output, and also to ensure that the output is of the plan follow the target reference output, and the MPC controller use that is called an optimizer. Okay, this prediction strategy uh, based on the based on the use of the plan use, which is we call a car model by MPC controller to simulate the car part in the next P, which is the state time, where P is in the prediction horizon, which represent the time, and the MPC controller look forward in the future to make the prediction. Okay, next, the optimization problem. The MPC controller solve an optimal visual solution at each control interval, which is a quadratic problem. For specific, the following are part of the optimization problem. For the first one is cost function. Cost function is also known as the objective function because it measures the controller performance to decrease it. Next is constraint. Constraint is define the soft and hard iteration that constraint must fulfill the for the system requirement to be met, including the physical bounds. And the last one is decision. Decision is meant to modify the controller variable to minimize the cost function and meet the iteration. Okay, another part is we move to the methodology. We start to designing an MPC model for autonomous steering system. That we create a custom reference trajectory using driving scenario designer toolbox. And the next one is we tuning an MPC controller for the parameter like I mentioned before. We change the 3 parameters inside the parameter MPC controller, which is the step time, prediction horizon, and control horizon. For the constraint, we change the value of we tuning the value of steering angle and steering angle changing rate. And after we tuning the MPC controller, we evaluate the tuning response from MPC controller. If they get a certified value from that graph, we move to the compare the default response with tuning response for lateral position and your angle. If not, we tune back the MPC controller until we get a certified result. Okay, for the after the evaluate tuning, we move to the comparison of the default response. Okay, like I mentioned before, for the first our first objective is to evaluate the tuning response. So in evaluate tuning part, you can meet the objective one. And for the another part is another objective we made to either compare the default response with tuning response for the lateral and position angle. Okay, this is for the objective 2. Then after we get a comparison between these two lateral position and your angle, we end of the project methodology. Okay, this is our MPC model for an autonomous steering system. That we start with the reference that I mentioned before. Reference is a custom reference that we create from the scenario custom trajectory that we made from the scenario toolbox. Okay, then we move to the MPC controller. Inside the MPC controller, we have a multi-output, which is in this case, we have two output, which is a lateral position and yaw angle, so that you can calculate the output. Then from the MPC, we have a steering angle, so we move to the plan, which is the car model. Then the car model become a two output, like I mentioned before, lateral position and yaw angle. Okay. Okay, next, this is what I taught before. This is the create custom reference trajectory using a driving scenario design toolbox. Okay, this is how I tuning the MPC controller, like I just mentioned before. We put the default parameter inside the car model. For the MPC controller, we put a sample time at 0.1 second. For the prediction horizon, we put a 10 second, and control horizon, we put a 2 second. Next, we move to the constraint parameter. For the steering angle, we put a -2 and 6 radian, and steering angle for changing rate is 0.2 and -0.2 and 0.2 radian. Okay, this part show how I evaluate and compare the default response with tuning response for the lateral and the yaw angle. As you can see here, these two scope represent the graph that I need to investigate and compare. So when after I run the system, I can expose the graph from these two scope. Okay, for the next part, for the last part of this proposal project is I will show you the preliminary result. As you can see here, there are two graphs from these two scope. Okay, for the first graph is represent the lateral position graph, and the second graph represent the yaw angle. There are two color. There are two legend inside the graph. For the yellow one, it represent the output, and the blue one it represent the reference that we create from custom trajectory, so that we can investigate and make a comparison between the output and the reference trajectory that we made from the designer toolbox. So for this result, in fact, the changing the prediction horizon is to find the optimized trade-off size of matrix with computational load, and for the control horizon is to find optimized trade-off system dexterity, which is react quickly for the variation with computational load. Okay, for the further research, I will overcome the objective 1 and objective 2. This is only for the preliminary result for this proposal. Okay, I hope I deliver well for this project proposal. Thank you very much for watching this video project proposal. Uh, thank you to our panel, which is Dr. Rashid and Safizi. Thank you.